I remember when I first saw this stuff so long ago, I didn't get it at first either. Math doesn't come easily to me, okay? It doesn't. But that's expected. That's okay, though. Okay. I'm on, All right, anyway, let's keep going. So this is a new kind of function. Notice where the input is, the x, right? That's the exponent. Right? In other words, our function now, f of x, is by definition 1.05 raised to the x. Not times x as over here, or plus x, the exponent is x. There's a reason why I rewrote it like this. You'll see shortly. Okay, so let's calculate some, function values. When x is 0, the function is going to be 1. Any non-zero number raised to the 0 power is always going to be 1. In Math 104, I actually proved that. It's not hard to show. It's just based on properties of exponents. When x is 1, here we'll have 1.05 to the 1, which is this. I rounded it to 6 decimal places to be consistent. And then when x is 2, you get this function value. When x is 3, you get this. And when x is 4, you get this, and so on. Remember, you're raising it to the exponent. You're raising it to the x. So for 2, this is 1.05 squared. This is 1.05 cubed, raised to the 3rd power, that is. Okay. And by now you probably saw this column. So here I'm looking at by how much the output is changing. Well, here you can see it's increasing by 0.05 as x goes from 0 to 1. As x goes from 1 to 2 here, right? The function outputs is increasing, right, by this amount, which is not the same as this. It's increasing by more. So the output is changing by more, not by the same amount as here. Here also, f of 3 minus f of 2 is not the same, is not a constant. It's not the same value as here or here. In other words, this function is not linear, is what I'm trying to say. If you increase your input, your x, by 1, the change in output is not always going to be the same. With linear functions, it is. That's what the slope is. Here, that's not happening, right? The output, the change in output is getting bigger. But there is something else going on here. Let's look over here. Notice here, what I'm doing is I'm calculating relative change. What I'm doing is I'm treating f of 0 here, f of x that is, let me say it here. For when x is 0 and 1, I'm treating f of 0 as the starting value, f of 1 is the ending value. So as x goes from 0 to 1, we're calculating the percent change in output, which is 5%. As x goes from 1 to 2, the output changes, it increases by 5%. As x goes from 2 to 3, right? This is the percent, this is the change in output, the percent change in output, well, the relative change, but then we convert it to a percent. The output is increasing by 5%. So here with linear functions, if we increase x by 1, the output changes by m, the slope. Here, however, it's changing by a constant percent. The function values are increasing by 5%. And that's what I'm saying here. So we don't have a constant rate of change. What we have is what's called a constant percent change. Namely, the percent change is 5%, which as a decimal is 0.05. 0.05. Look what I'm doing also. I wrote it this way. Okay? That's no accident. This 0.05 here, if I change it to a percent, 5%. The function outputs are increasing by 5%. This is actually what we call an exponential function. We have an exponential function or an exponential growth or decay function. This is a function that's either growing or shrinking at a constant percent growth rate. In other words, the function values are changing. They're increasing or decreasing at a constant percent rate. That's what's happening here, right? We have a constant percent change in output. And those functions in general are going to look like this. We have a times b raised to the x. A is just a constant, but it turns out to be f of 0, the initial value, or the starting value, in other words. Okay, so in this example here, the a was just 1. I mean, we didn't write it, but that's okay though. Usually, again, if you have a coefficient of 1, people don't write it. For b, though, that's our base. It's also called the growth or decay factor. It's the growth or decay factor. It turns out that b has to be positive, and it can't be 1. If b was 1, then you would have a times 1 to the x. But 1 to anything is just 1, so that wouldn't be very interesting. It would be just a constant function. And basically what's happening with exponential functions, if your b, your growth factor, is greater than 1, the function is increasing and you have growth. And that's actually what we had here. This is our b, 1.05, which is bigger than 1. And as you can see, the function values are growing. They're increasing, growing in value. So we had growth here. If b, however, were positive but less than 1, then the function would be decreasing or decaying. Okay, now this is useful, but I'm going to write this in a more useful form, namely here. So if r is that percent growth rate or decay rate, but in decimal form, so in other words, r is the constant percent rate that the function output is increasing by, but written as a decimal, we can write, okay, the exponential function this way if we have growth, or this way if we have decay. And this is just saying what I said before, that a function in this form, this exponential function, it's either increasing as here or decreasing here at a constant percent growth rate, that's here, or decay rate here. It's basically changing at a constant percent rate. And that constant percent rate is r percent. R times 100%, excuse me, because r is a decimal, so you have to convert it to a percent. So going back to, where is it? This example, r was 0.05. This would have been our r. So the function values here, these are growing. That is, let me say this, r 0.05, okay? So this function is an exponential function. The percent growth rate would be r as a decimal, and r in this case is 0.05. I wrote this here because when you convert it to a decimal, convert it to a percent, right? You have to you move the decimal 2 spaces to the right. That's equivalent to multiplying by 100. And this is what's just going to happen, just like in the first example. This is, again, just showing you that the function outputs, if you increase x by 1, the function values are going to change by r%, where, again, r is a decimal, so you convert it to a percent. Okay, that's probably a little confusing. I understand it is. Does everyone kind of understand? Are there any questions so far at all? You know what? Here, no, wait. Here's a better way of asking it. I know this is new, so it may not make sense at first, but that's why we're going to do examples. Okay. Yeah, some people are saying no, but that's okay. Okay. I think when we do more examples, it'll click a little bit better. I know this stuff is a little tricky. I understand. Okay. All right. Okay, so let me do the recording.